Chairman, for your introduction. My presentation is concerned with the characterization of a new aluminum alloy containing chromium for the production of light alloy wheels by Hybrid Aluminium Forging, an innovative technique. During my speech, I will cover a short introduction about the process of the alloy, then I will present the main methods applied and the main results achieved, and finally conclusion and future activities. The main technologies for the production of light alloy wheels are low-pressure die casting and forging. Low-pressure die casting is a cost-effective process which can ensure high productivity and the possibility to produce wheels with complex geometric shapes. On the other hand, the mechanical properties of cast wheels are not as high as those of forged wheels, and this is indeed the most important features of this other process. Forged wheels cannot have such a complex shape as cast wheels, and also the process requires higher cost and so a lower production rate. So it's easy to understand how a process which can keep the advantages of these two techniques and try as much as possible to overcome the defects could be really effective and really interesting for the automotive field. This is not a new idea, and the HAF process is one of the possible processes which try to combine the two processes together in order to overcome the defects and keep the advantages. Indeed, this process mainly consists in two phases. The first one, during the first one, the mold is closed and is filled as in low pressure die casting. As a second step, the feeder tube is closed, and then the upper part of the mold is used to apply a forging pressure on the material during the solidification, so when the material is not still completely solidified. In this way, it is possible to reduce the presence of porosity, to reach a faster solidification and so a finer microstructure, and this can help in the improvement of mechanical properties. At the same time, it is still possible to have wheels with a complex geometric shape, and also another important characteristic is the possibility to have a process which is cost-effective and which can ensure a high production rate. But it is not possible to achieve these goals by just combining these techniques. Indeed, it is fundamental to use the most suitable material. The time being, the alloy under study and which is used in a pilot plant scale, it's an alloy containing silicon, magnesium, and chromium addition with the content shown in the table. The silicon content is between the typical values for cast wheels, usually 7% of silicon, and forged wheels, sometimes also below 1% of silicon. Then magnesium is present as a strengthening element after heat treatment. Chromium instead is the non-conventional alloy elements with a strengthening effect. And finally, it's also iron is present, but it's an impurity typical of aluminum alloys. So the aim of this project is the characterization of this alloy for the production of wheels by the HAF technique. The experimental procedure. First of all, we perform these measurements to identify the temperature range for the application of the forging pressure, then mechanical characterization and microstructural observation with conventional techniques, and finally we perform also rheological measurements to better understand the suitability of this material for the process. The results will compare with typical value of cast wheels and forged wheels. So, from the DSC curves, it was possible to calculate the solidus and liquid temperatures and the value are shown in the table. Then, from the integration of the DSC curves, it was possible to calculate the solid fraction curve, so the solid fraction behavior against temperature. This was really important to understand which is the temperature range during it was possible to apply the forging pressure. Because It is applied between the liquidus temperature and the 70% of solid fraction. So for this alloy we have a temperature range of 30 degrees between 610 and 640 approximately. Then for further characterization, samples were taken from wheels actually produced by this innovative technique, both from as-cast wheels and heat-treated wheels, and samples were taken from different parts along the wheel section. The tensile properties show, it is possible to see from this plot, that ultimate tensile strength and yield strength are really improved if compared to the performances of cast wheels, and the values are really similar to those of forged wheels. On the other hand, the elongation is the critical parameter because the elongation values were less than the performances of both cast and forged wheels. In order to understand the reason behind this behavior, we detected by microstructural observation the presence of intermetallic phases containing, as it is possible to see from the table, iron and chromium. These intermetallic phases show not the typical morphology of iron intermetallics, that is the needle-like morphology that is typical from cast wheels, but a more complex morphology, a star-like or Chinese script morphology, which is known to be less detrimental for mechanical properties. So this is supposed to have a strengthening effect of the product, for the product. From instead the observation by SEM of the surface fracture, it is possible to detect a mainly ductile morphology of the fracture, and also the presence of intermetallics containing chromium and iron. They detached from the matrix but did not crack, so helping the ductile mechanism of the fracture. For comparison, we analyzed also samples from the same wheels but without the chromium addition. We found a similar general mechanism of the fracture, but in addition we found different intermetallics. So, as it's possible to see in figure E, an iron intermetallic particles which cracked instead. So it is not possible to link the low ductility of the product to the presence of chromium, or but more likely this is due to still the need to improve the process, which is just a pilot plant, in order to avoid the presence of defects, and also the need to optimize the heat treatment parameters in order to find a better balance between test strength and elongation. Finally, we performed also rheological measurements, always in semi-solid condition, so with a 40% of solid fraction. We detect a shear thinning behavior in semi-solid condition, that is that the viscosity decreases, increasing the viscosity decreases, increasing the shear rate, and this is positive because it can enhance the effect of the forging pressure during the process. So in conclusion, we can say that the GF technology is a promising process that will show, for sure, a high tensile strength, very close to that of forged wheels. That chromium is mainly responsible for the modification of intermetallic phases from a needle-like that is more detrimental to a Chinese script morphology, which is instead less harmful. Then also the rheological behavior is positive, but still ductility is the critical parameter. So as a future activity, the optimization of the process and of the treatment will be carried out, and also it will be evaluated the possibility to still optimize also the alloy composition. And then also the analysis of the precipitation sequence by DSC and ETM analysis will be carried out. Thank you for your attention.